The Pacific Ocean has a name that means peaceful. Ferdinand Magellan gave it that name in 1520 after he crossed it during his round-the-world voyage and found nothing but calm water and gentle winds for weeks on end. He was thrilled. He called it Mar Pacifico, the peaceful sea, and that name stuck for 500 years. It is one of the biggest lies in the history of geography. 90% of all earthquakes on Earth happen here. Not most, not the majority, 90%. Every major tsunami in recorded history started here. The ocean floor is actively swallowing itself. Right now, as you watch this, slabs of crust the size of continents are sliding down into the mantle at speeds measured in centimeters per year, dragging stress and heat and pressure with them until something breaks. And the cities sitting on the edges of this ocean, Seattle, Tokyo, Jakarta, Lima, Auckland, have millions of people living their daily lives within reach of forces that could flatten entire coastlines in under 10 minutes. This is not a story about rare disasters. This is a story about the most geologically violent region on the planet, why it works the way it does, and what it means that roughly 3 billion people live in its shadow. If you've ever wanted to understand why the Earth shakes where it does, why tsunamis can cross an entire ocean and still kill people on the other side, and what scientists have found buried in ancient forests and ocean sediments that keeps them up at night, you're in the right place. Subscribe and hit the bell so you don't miss the rest of this one, because what's coming in this video is going to change how you look at every coastline you've ever stood on. Now, the Ring of Fire. You've probably heard the name. It sounds dramatic, maybe a little exaggerated. It isn't. If anything, the name undersells what it actually is. Picture a line, or more precisely, a horseshoe, stretching 40,000 kilometers around the entire Pacific Basin. Start at the southern tip of South America. Follow the Andes north through Chile, Peru, Ecuador, Colombia. Keep going up through Central America, Mexico, California, Oregon, Washington. Cross into Alaska and arc west along the Aleutian Island chain. Drop down through Kamchatka and the Russian Far East, through Japan, through the Philippines and Indonesia, all the way to New Zealand. That's the Ring of Fire. That's the outline of the most seismically and volcanically active region on Earth. Along that 40,000-kilometer chain sit roughly 450 volcanoes, more than 3/4 of all active volcanoes on the planet. Of the 25 largest volcanic eruptions in the last 11,000 years, only 3 happened outside this zone. 80% of the world's largest earthquakes occur here. The deepest ocean trenches on Earth form here. Some of the most fertile farmland on the planet sits here, on the slopes of volcanoes whose ash has been enriching soil for millennia, which is part of why people keep living right next to them, even when they know what those mountains can do. But the name, dramatic as it is, only tells you where the danger is. It doesn't tell you why. And the why is where the story gets genuinely strange. To understand why the Pacific is different from every other ocean on Earth, you have to go back to an idea that spent 40 years being treated as scientific nonsense. Alfred Wegener was a German meteorologist who noticed something that a lot of people had noticed before him, that the eastern coast of South America and the western coast of Africa look like they could fit together, like 2 pieces of a jigsaw puzzle. He published this observation in 1912, along with a theory he called continental drift. His argument was that the continents had once been joined together in a single supercontinent he called Pangaea, and that they had slowly moved apart over hundreds of millions of years. The geological establishment's response was swift and almost unanimous. No. The main problem was mechanism. Wegener could describe what he thought had happened, but he couldn't explain how. What force could possibly move an entire continent through solid rock? The idea seemed to violate basic physics. At a 1926 symposium held by the American Association of Petroleum Geologists specifically to address the continental drift hypothesis, geologist after geologist stood up to dismiss it. One called it a fairy tale. Another said it was utter damned rot. Wegener himself was not a geologist. He was a meteorologist. And that made it easy for the establishment to dismiss him as an outsider who didn't understand the field. He died in 1930 during an expedition to Greenland, still largely rejected by the scientific community he'd spent his career trying to convince. The proof he never found came from the ocean floor, and it came from an entirely unexpected direction. In the 1950s, a geologist named Marie Tharp began mapping the floor of the Atlantic Ocean using data from depth soundings collected by ships. The maps she produced were stunning. The ocean floor wasn't flat. It had mountain ranges, valleys, ridges, a landscape as complex as anything on land. Running down the center of the Atlantic, she found a continuous ridge, a seam in the ocean floor stretching thousands of kilometers. Then came the detail that changed everything. In the early 1960s, surveys of the ocean floor began detecting magnetic striping, alternating bands of rock magnetized in opposite directions, running parallel on both sides of the mid-ocean ridges. The pattern was symmetrical, like a mirror image on either side of the seam. Once researchers understood what they were looking at, the explanation was almost impossible to argue with. The ocean floor was spreading. New crust was being created at the mid-ocean ridges, where molten rock welled up from the mantle and hardened. As it hardened, it locked in the direction of Earth's magnetic field at that moment. As Earth's magnetic field periodically reversed, which it does over geological time, the new crust recorded those reversals in sequence, creating stripes. The symmetrical pattern on both sides of the ridge proved that the seafloor was moving outward from the center in both directions, like a very slow conveyor belt. And if new ocean floor was being created in the middle, somewhere it had to be destroyed at the edges. This is where the Pacific comes in. This is where the whole picture snaps into focus. The process has a name: subduction. Once you understand what subduction actually does, the ring of fire stops being a mystery and starts being a logical consequence of how the planet works. First, the descending slab doesn't go quietly. The two plates are in contact for hundreds of kilometers along what geologists call the subduction interface, a zone of friction where rock is trying to slide past rock under enormous pressure. Most of the time, the plates are locked, stuck together by friction, building stress the way a compressed spring builds tension. When that lock fails, when the accumulated stress overcomes the friction holding the plates together, the fault ruptures. The overriding plate snaps back. That snapping releases energy that propagates outward through the Earth as seismic waves. The bigger the fault, the longer it's been locked, the more energy is released. The result is an earthquake, sometimes a very large one. Second, as the slab descends deeper into the mantle, it carries water with it. Water locked in the minerals of the oceanic crust. Water in the sediments draped over the slab. Under the heat and pressure of the deep mantle, that water is released. Water lowers the melting point of rock. The mantle rock above the descending slab begins to melt. The molten rock, magma, is less dense than the surrounding material, so it rises. It punches through the overriding plate. It builds volcanoes. This is why volcanic arcs sit parallel to the trenches. Japan sits above the subducting Pacific plate. The Cascade volcanic range in the American Northwest sits above the subducting Juan de Fuca plate. Indonesia's volcanoes sit above the subducting Indo-Australian plate. The geometry is the same everywhere. Trench at the edge, volcanic arc above the point where the slab has gone deep enough to release water and generate melt. The Pacific plate is the largest tectonic plate on Earth. It covers roughly 100 million square kilometers. And it is moving westward and northward at roughly 7 centimeters per year along different sections of its boundary. That's about the speed your fingernails grow. But over millions of years, 7 centimeters per year is enough to build mountain ranges, carve ocean trenches 11 kilometers deep, and run a geological engine that accounts for the overwhelming majority of seismic energy released on this planet every year. The sheer scale of the subduction happening around the Pacific is almost impossible to compress into a single image. Along the western Pacific alone, from Kamchatka down through Japan, the Ryukyu Islands, Taiwan, the Philippines, and into Indonesia, multiple plates are converging, overlapping, diving. The Philippine plate is being consumed beneath the Eurasian plate. The Pacific plate is diving under Japan at roughly 8 centimeters per year. The Australian plate is colliding with the Pacific plate along a boundary running through Papua New Guinea and the Solomon Islands. Each boundary is its own seismic engine, its own chain of volcanoes, its own source of tsunamis.
On the eastern Pacific, the pattern repeats on the American side. The Juan de Fuca plate, a small remnant of a much larger ancient plate, presses against the North American plate along a fault system called the Cascadia Subduction Zone. The Nazca plate grinds under South America, building the Andes and loading stress onto some of the most seismically dangerous fault lines on Earth. This is the planetary machine that Wegener glimpsed without understanding, that Tharp's maps began to reveal, that the magnetic striping confirmed, and that seismologists have been studying in increasingly fine detail ever since. The more precisely they study it, the more clearly they see that the Ring of Fire is not a collection of separate, unrelated geological events. It's a single, interconnected system. A loop of crust creation and destruction that has been running for 250 million years and shows no signs of stopping. Which brings us to what that system is actually capable of when it decides to move. On the 22nd of May, 1960, the ground along 1,000 kilometers of the Chilean coast began to shake. The earthquake that followed registered a magnitude of 9.5. No earthquake in recorded human history has been larger, before or since. The ground did not shake for the usual 20 or 30 seconds. It shook for roughly 10 minutes. 10 minutes of continuous, violent ground motion across a region the size of California. Towns along the coast watched the ocean drain away from the beach, the classic warning sign that nobody in 1960 knew to run from. And then, the water came back. The first wave hit Valdivia at 9 meters. The city was already half destroyed by the earthquake. The tsunami finished it. 800 kilometers of Chilean coastline was, as one account described it, essentially erased. The story of the 1960 Chilean earthquake doesn't end in Chile. It couldn't, because water doesn't care about borders. The tsunami radiated outward across the Pacific at the speed of a jetliner, around 700 kilometers per hour in open water. At that speed, the waves are barely visible from the surface, stretched out across hundreds of kilometers of ocean. They're almost impossible to detect without specialized instruments. They lose almost no energy crossing open ocean. What they lose in height in deep water, they regain as they approach shallow coastlines. the waves stacking up as the seafloor rises to meet them. 15 hours after the earthquake in Chile, waves 4 to 6 meters high struck Hilo, Hawaii, destroying the waterfront and killing 61 people. A warning had been issued. Some people evacuated. Some didn't, partly because a false alarm 2 years earlier had eroded public trust. 22 hours after the earthquake, waves up to 6 meters high struck the coast of Japan, on the opposite side of the Pacific Ocean, 10,000 kilometers from the epicenter. 138 people were killed. Waves reached the Philippines, the Aleutian Islands, and the coast of California. A single rupture of the ocean floor off South America killed people across 14 time zones. What the 1960 earthquake revealed was the true scale of a megathrust rupture. The Nazca Plate had locked against the South American plate for centuries, building stress along a fault zone extending over 1,000 kilometers in length. When it released, the displacement wasn't a matter of a few meters of slip on a small patch of fault. 20 meters of slip across a fault the length of California, and then some. The energy released was equivalent to roughly 25,000 atomic bombs of the type dropped on Hiroshima. Seismologists now had a number for what the worst could look like. And they started looking at other subduction zones around the Pacific with new urgency, asking the same question. Where else is stress accumulating on a locked fault? And how long has it been building? The answer they found on the western coast of North America was, to put it mildly, alarming. The Cascadia Subduction Zone runs from northern California to southern British Columbia, roughly 1,000 kilometers of convergent fault, where the Juan de Fuca Plate is pressing beneath the North American Plate. For most of the 20th century, geologists believed Cascadia was different from other subduction zones. The fault seemed quiet. There were small earthquakes, but nothing like the great megathrust events seen in Chile, Alaska, Japan. The assumption, never quite stated but widely held, was that perhaps Cascadia released stress gradually rather than catastrophically. Perhaps the Pacific Northwest was safer than it looked. Then, a geologist named Brian Atwater started digging in the mud. In the mid-1980s, Atwater was working along the coast of Washington state, studying coastal wetlands. What he found in the sediment layers stopped him. Buried beneath meters of mud and peat, he found ancient soil horizons, layers of organic material that looked like they had once been coastal meadow, then been suddenly dropped below sea level and buried under marine sediment. The pattern was consistent with what would happen if the coastline suddenly subsided during a major earthquake and was then inundated by the sea. He found these layers at site after site along the Washington and Oregon coasts. They appeared simultaneously across hundreds of kilometers of coastline, suggesting a single, simultaneous event. The radiocarbon dating of the buried organic material pointed to a date around the year 1700. The geological record in the coastal sediments was telling a story. And then, Atwater found confirmation from an entirely different source. Japanese historical records from January 1700 described a tsunami arriving on the coast of Japan, with no corresponding earthquake in Japan to explain it. An orphan tsunami, waves with no local parent. The timing of those waves, working backward across the Pacific, pointed to an earthquake off the coast of North America at around 9 in the evening on the 26th of January 1700. Further analysis of the sediment layers, tree rings from drowned forests preserved in coastal waterways, and the Japanese tsunami records together converged on a single conclusion. The entire Cascadia Subduction Zone had ruptured at once, producing a megathrust earthquake estimated at magnitude 9 or higher, and generating a tsunami that had crossed the Pacific and struck Japan without anyone in North America leaving a written record of what had happened. The fault had moved 20 meters,
The coastline had dropped by a meter or more over hundreds of kilometers. And no one living along that coastline in 1700 had any warning it was coming. Geophysicist Harold Tobin at the University of Washington, who has spent years studying the Cascadia Fault, put it plainly in a statement that made headlines when published. The zone is capable of generating a magnitude 9 or higher. Computer modeling suggests the resulting tsunami could reach 35 meters in height at certain points along the coast. The cities of Seattle, Portland, and Vancouver sit in direct proximity to this system. The infrastructure, roads, bridges, hospitals, power lines, is not built to withstand a magnitude 9. And the time between the earthquake and the first tsunami waves reaching coastal communities could be as short as 15 minutes. 15 minutes. The Cascadia story is a perfect illustration of how geological time and human time don't communicate well with each other.
300 years of quiet is an eternity to a city planner, and a geological eye blink to a fault system. The absence of a catastrophe in living memory creates the impression that no catastrophe is coming. It's the same psychological pattern that kept farmers living on the slopes of Vesuvius for a century after the last eruption. The same pattern that keeps millions of people in Jakarta and Seattle and Osaka going about their lives within reach of some of the most dangerous geology on Earth. The Cascadia Fault is not alone. The same question, how long has the stress been building, and when does the next rupture come, is being asked at every subduction zone around the Pacific. Some of them have already answered it in the most devastating way possible. What scientists learned studying the buried forests of Washington State and the ancient Japanese records would prove to be more than academic. It became the template for understanding every locked fault on the Pacific Rim. Because the pattern Atwater uncovered, centuries of silence, then catastrophic rupture, then silence again, is not unique to Cascadia. It repeats, with local variations, at every major subduction zone on Earth. And the consequences of misreading that silence, of mistaking geological quiet for geological safety, would be demonstrated again on a December morning in 2004, in a way that left no room for doubt. The 22nd of May, 1960, Valdivia, Chile, 5:13 in the afternoon. A fisherman named Jose Penicur was mending nets on the dock when the shaking started. He had felt earthquakes before. Everyone in southern Chile had. The country sits directly above the Nazca Plate, and small tremors were part of the background noise of life there, the way thunder is part of summer. But what started at 5:13 that afternoon was different from the first second. The dock began moving under his feet, like the deck of a ship in a storm. Except there was no storm, and there was no wave. The ground itself was liquid. Wooden buildings along the waterfront began to collapse, not from any impact, but simply from the sustained impossibility of remaining upright while the earth beneath them refused to hold still. The shaking lasted 10 minutes. Think about what 10 minutes of continuous, violent motion actually means. A normal, strong earthquake shakes for 20, maybe 30 seconds. 1 minute feels like an eternity when the ground won't stop moving. 10 minutes is geological time colliding with human time in the most visceral way imaginable. Walls that survived the first 30 seconds could not survive the next 30. Walls that survived that could not survive the next 30 after that. By the time the ground finally settled, large parts of Valdivia had simply ceased to be buildings. They had become rubble fields. And then the ocean drained. People standing on what remained of the waterfront watched the sea pull back from the coast
like an enormous curtain being drawn. Boats that had been floating in the harbor were suddenly sitting on exposed mud. The sea floor was visible, where minutes before there had been several meters of water. Some people ran toward the retreating ocean out of sheer disbelief. Some ran because they could see fish flopping in the sudden shallows. Researchers who studied survivor accounts later noted that in 1960, almost no one on the Chilean coast knew what a retreating sea meant. There was no public education about tsunamis, no warning system, no culture of evacuation. The water came back at approximately 9 meters. The first wave hit Valdivia and the surrounding coast and took what the earthquake had left standing. The second and third waves followed within minutes. The city of Puerto Montt was hit, the town of Lebu.
Fishing villages along 800 kilometers of coastline were inundated. The final death toll from the earthquake and tsunami combined was somewhere between 1,600 and 6,000 people. The range exists because in many coastal villages, there was simply no one left to count. But the Pacific was only beginning to carry this energy outward. At the speed of a commercial jetliner, the tsunami waves spread across the ocean in all directions simultaneously. In open water, they were nearly undetectable. Long, low swells stretched across hundreds of kilometers, carrying enormous energy in a form that passes beneath ships without those on board feeling anything. The physics of ocean waves in deep water means speed and wavelength are inversely related to height. In the middle of the Pacific, the waves from the Chile earthquake were perhaps half a meter tall and hundreds of kilometers long. They were invisible threats, moving at 700 kilometers per hour. 15 hours after the rupture, they reached Hilo, Hawaii. A warning had been issued. Some people evacuated. Some didn't, partly because a false alarm 2 years earlier had eroded public trust in the warning system. The waves that hit Hilo's waterfront reached 6 meters in places. 61 people died. The commercial district along the bay was demolished. Photographs taken in the aftermath show entire city blocks reduced to concrete slabs, cleared of everything that had stood on them as thoroughly as if swept clean with a hand. 22 hours after the earthquake, on the other side of the planet, across the largest ocean on Earth, the waves reached Japan. On the Sanriku coast of northeastern Japan, communities that had survived their own tsunamis over centuries stood on shore as water arrived from 10,000 kilometers away. The waves reached heights of 4 to 6 meters along sections of coast. 138 people died. Hundreds of homes were destroyed. The fishermen and families of the Sanriku coast had lost their lives to an earthquake they had never felt, in a country most of them had never seen, on a fault they had no reason to know existed. The 1960 Chilean earthquake forced geologists to completely revise their understanding of what a subduction zone was capable of. Before it, the largest instrumentally recorded earthquake had been around magnitude 8.9. The concept of a magnitude 9 event was theoretical. After Valdivia, it wasn't theoretical anymore. It was a documented reality with a body count attached. And the question that followed, where else could this happen, would take decades to answer. And the answers, when they came, would consistently be worse than anyone had hoped. Among the scientists who began asking those questions was a young geologist who came to the problem not through data or instruments, but through something much more personal, through survival. Harry Glicken was a graduate student at the University of California, Santa Barbara in 1980 when he was assigned to work with David Johnston, a volcanologist with the United States Geological Survey monitoring Mount St. Helens in Washington state. The volcano had been showing signs of unrest since March of that year. Small earthquakes,
a growing bulge on its north flank, steam emissions. Johnston had set up an observation post roughly 8 kilometers from the summit, on a ridge called Coldwater Ridge, and the two men had been trading shifts there through the weeks of unrest. In mid-May, Glicken needed to leave the observation post to attend a review session connected to his graduate program. Johnston took over the shift for him on the morning of the 18th. At 8:32 that morning, a magnitude 5.1 earthquake triggered the collapse of Mount St. Helens' north flank, the largest landslide in recorded history. The collapse depressurized the magma chamber beneath the bulge instantly.
What followed was not a vertical eruption. It was a lateral blast, a sideways explosion that shot outward at roughly 400 kilometers per hour, flattening everything within a zone of nearly 600 square kilometers. The blast overtook the landslide. Trees were snapped or stripped at a distance of 20 kilometers from the crater. The ash column rose 24 kilometers into the atmosphere. David Johnston had time to radio one message before the blast reached him. "Vancouver! Vancouver! This is it!" His body was never found. Harry Glicken survived because he had a review session to attend. He spent the rest of his career in a state that colleagues described as compulsive dedication bordering on obsession. He returned to Mount St. Helens and studied it exhaustively, documenting the 1980 eruption in extraordinary detail, trying to understand exactly what the mountain had done and why the warning signs had not been sufficient to predict the precise character of the eruption. His work on the deposit left by the lateral blast and the landslide became foundational. He helped establish the science of volcanic debris avalanches, documenting how the failure of a volcanic edifice could trigger destruction on a scale and in a direction that no one had anticipated. What Glicken kept returning to, in his published work and in conversations with colleagues, was the problem of warning time. Mount St. Helens had shown signs of unrest for 2 months before the eruption. Geologists had monitored it intensively, and still the precise moment and mechanism of the eruption had not been predicted. The lateral blast, the killing mechanism, was not something the models had fully accounted for. Johnston had been inside what the scientists believed were safe parameters. The mountain had simply done something the models hadn't anticipated. This became Glicken's core message to the field. Volcanoes do not behave reliably like their models. They retain the capacity for surprise even under close observation. The data tells you a mountain is restless. It doesn't always tell you what form the violence will take. He moved to Japan in the late 1980s to continue his research at the Hokkaido University Institute of Seismology and Volcanology. On the 3rd of June, 1991, he was part of a team of scientists and journalists observing Mount Unzen in Kyushu, Japan, which had been producing pyroclastic flows, fast-moving currents of hot gas and volcanic matter. The team was positioned at what they calculated was a safe distance, based on the observed behavior of previous flows over the preceding weeks. The flow that came down the mountain that afternoon traveled further than any previous flow had gone. Harry Glicken was killed along with 42 other people, including 2 French volcanologists who had survived dozens of previous close observations of eruptions around the world. He was 33 years old. He had survived Mount St. Helens by a matter of scheduling, and he had spent the 11 years between that survival and his death trying to ensure that others would not have to rely on luck in the same way. What his work left behind was a set of principles that volcanic hazard scientists still use. Among them, the irreducible idea that historical patterns of behavior are a starting point, not a guarantee, and that the safe zone around an active volcano must always be larger than the data alone suggests. The scientists who came after Glicken carried that principle into every discipline touching on geological hazard, including the study of subduction zones. And nowhere was that principle more consequential, or its absence more catastrophic, than in the question of what happens
when a major subduction zone ruptures in an ocean where no one had built a warning system.
When Brian Atwater first waded into the coastal wetlands of Washington state in the mid-1980s, he wasn't looking for evidence of a prehistoric megathrust earthquake. He was studying how coastlines respond to gradual sea level change. What he found instead was evidence of something violent and sudden. At Willapa Bay, at Gray's Harbor, at dozens of sites along the Washington and Oregon coasts, the sediment told the same story. Layer after layer of peat, the compressed remains of coastal meadow, the kind of dense, root-bound organic mat that takes centuries to develop, was capped by a sharp boundary. Above that boundary, gray marine mud, the kind deposited under open water. The transition was abrupt. Not gradual, the way a slowly rising sea would leave it, but instantaneous in geological terms. The meadow had existed. Then it had been below the sea. Then marine sediment had buried it. The interpretation was stark. During a major subduction zone earthquake, the overlying plate doesn't just shake, it snaps. When the locked fault releases, the coastline above the rupture zone can drop suddenly, sometimes by a meter or more, as the elastic energy stored in the compressed rock releases all at once. Coastal meadows that had been at sea level became intertidal mudflats or open water overnight. The marine mud that buried them was deposited in the years and decades afterward. Atwater kept finding the buried horizons. Site after site, the same sharp boundary. And when he sent samples for radiocarbon dating, the ages clustered around the same period, the late 17th century. Then came the ghost forests. Stands of old cedar and spruce trees rise from tidal waters along certain coastal rivers in Washington and Oregon, their trunks gray and stripped of bark, their roots still anchored in the ground where they had grown for centuries. Killed when the land they stood on dropped below the salt water line and tidal flooding overwhelmed them. Some of these trees had been dead for 300 years. Their wood, preserved in the cold, oxygen-poor tidal water, still held growth rings that could be dated. The outermost rings, the last years of growth before death, pointed to the late 1600s. The trees had died suddenly, all at once, in a saltwater inundation that gave no warning. Atwater's findings began to attract serious attention. Other researchers joined the work. Geologists in Oregon found the same buried horizons. Researchers began examining native oral traditions. The Hu-Ayat people of Vancouver Island had a story about a great shaking of the earth and walls of water that destroyed villages along the coast. The Quileute of the Olympic Peninsula carried similar accounts. The Tillamook had stories of a flood that came after the earth moved. These oral traditions had been recorded by ethnographers decades earlier, but had never been placed in the context of geological evidence. Now they were. They aligned with everything the sediment was saying. And then came the piece of evidence that Atwater himself has described as the most striking confirmation of all. Japanese historical records from the year 1700 contained accounts of a tsunami arriving on the Sanriku coast during the night of the 27th of January, 1700. The waves were described in detail. They caused damage and some deaths, and crucially, there was no local earthquake to explain them. Japanese seismologists, examining these historical records, reached out to Atwater and his colleagues. The timing matched. Working backward from the arrival time of the waves in Japan, researchers calculated that the earthquake generating them must have occurred off the coast of North America at approximately 9 in the evening on the 26th of January, 1700. The ghost trees, the buried meadows, the native oral traditions, the Japanese orphan tsunami. 4 independent lines of evidence from 4 different disciplines in 2 countries, all pointing to the same night. The Cascadia Subduction Zone had ruptured in a full-length megathrust event, magnitude 9 or higher. 1,000 kilometers of fault had moved at once. The coastline had dropped. The tsunami had crossed the Pacific in hours. And then came centuries of silence. Silence that the cities of Seattle and Portland and Vancouver would later mistake for safety. Atwater's work transformed Cascadia from a geological curiosity into a documented catastrophic hazard with a known recurrence interval. It didn't make the cities safer, it made the risk visible. And visible risk that doesn't produce action is, in its own way, a particular kind of tragedy. One that unfolds in slow motion, in budget meetings and building codes and evacuation drills that don't happen until the day the fault moves again and the silence ends. The tragedy of unacted knowledge was not hypothetical in December of 2004. It was not a future scenario. It happened. On a scale that remains almost impossible to absorb. On the 26th of December 2004, at 7:58 in the morning local time off the coast of northern Sumatra, a fault ruptured on the floor of the Indian Ocean. The Sunda megathrust, the boundary where the Indo-Australian plate dives beneath the Eurasian plate, the same subduction geometry as Cascadia, as Japan, as Chile, just in a different ocean. The rupture was magnitude 9.1. It lasted between 8 and 10 minutes. The fault displacement reached as much as 15 meters along parts of the rupture zone. The seafloor above the rupture lifted by several meters, displacing an estimated 30 cubic kilometers of seawater in a matter of minutes.
Within 15 minutes, the first wave struck the coast of Banda Aceh, at the northern tip of Sumatra. The waves reached heights of 30 meters in some locations along the Acehnese coast. They penetrated up to 5 kilometers inland, across flat terrain. The city was inundated. Entire neighborhoods were stripped to their foundations. Within 2 hours, waves struck the coast of Thailand. The tourist beaches of Khao Lak and Patong were crowded with visitors. Many of them saw the sea withdraw, the same warning sign that no one in Valdivia in 1960 had understood, and walked toward the waterline to look at the exposed seafloor, or to pick up stranded fish, or simply out of confusion. Some took photographs. The wave that followed was 6 to 10 meters high. It destroyed entire resort complexes. Within 3.5 hours, waves struck Sri Lanka. Within 4 hours, India's southeastern coast. Within 7 hours, waves reached the coast of Somalia, where they killed hundreds of people who had no connection to the earthquake, no knowledge it had occurred, and no reason to expect that their shoreline could be reached by an event 3,500 kilometers away. The total death toll was approximately 227,000 people across 14 countries. And this is where the scientific record becomes genuinely, morally difficult to process. Seismologists and oceanographers had known for decades that the Sunda megathrust was a major hazard. The subduction geometry was identical to zones that had generated the 1960 Chile earthquake and the 1964 Alaska earthquake, both of which had produced devastating transoceanic tsunamis. Academic papers had been written. Conference presentations had been made. The risk was documented in the literature. There was no tsunami warning system in the Indian Ocean. The Pacific Tsunami Warning Center, based in Hawaii, had been established after the 1960 Chile earthquake to monitor seismic activity and issue warnings when tsunamis were likely. It existed, it functioned, and it had protocols. In the Indian Ocean in 2004,
there was nothing equivalent. No network of deep ocean pressure sensors, no regional coordination center, no protocol for communicating warnings to coastal governments. Staff at the Pacific Center reportedly searched the internet for phone numbers for embassies and government agencies in the affected countries, trying to relay warnings through unofficial channels. Some warnings got through. Most didn't. The people on the beaches of Thailand and Sri Lanka and the coast of Somalia had no warning, not because the science had failed. The seismographs detected the earthquake within seconds of the rupture. Scientists knew what had happened and roughly what would follow. The warning infrastructure, the buoys, the protocols, the political will to build and maintain a coordinated regional network had simply never been built. A study conducted after the disaster found that a basic Indian Ocean warning system, combined with coastal community education, could have reduced the death toll by up to 80%. Not eliminated, reduced significantly. Instead, they died for the same reason that the people of Valdivia in 1960 had no warning. Not because the science didn't know, but because the knowledge hadn't been translated into infrastructure and action before the wave arrived. The 2004 disaster changed that. An Indian Ocean tsunami warning system was established within 2 years. Deep ocean buoys were deployed. Regional coordination protocols were written. Governments that had previously shown no interest suddenly found funding and motivation. Disasters are, in a perverse way, the most reliable driver of hazard preparedness the world produces. The knowledge exists before the catastrophe. The action comes after. This pattern, knowledge preceding catastrophe, action following it, appears at every point on the Ring of Fire where science has outpaced political will. And there is one country in the world that has experienced this cycle more times than any other, has been devastated more thoroughly by it, and has in response built a relationship with geological violence unlike anything else in human civilization. Japan has been shaped by the Ring of Fire for as long as Japan has existed as a culture. Its mythology contains the earthquake fish. Its architecture evolved around the assumption that buildings will fall. Its language has words for types of seismic shaking that have no direct equivalents elsewhere. Its people have drilled for tsunamis the way other countries drill for fire. And yet, in March of 2011, on the Senriku coast, the same coast struck by the Chilean tsunami in 1960, the same coast mentioned in the Japanese records of the Cascadia earthquake of 1700, the sea did something that even Japan was not fully prepared for. At 2:46 in the afternoon on the 11th of March 2011, a fisherman named Mikio Watanabe was standing on the dock at Kesennuma Harbor, unloading the morning's catch. He'd worked this dock for 30 years. He knew the sound of the water, the rhythm of the boats, the particular smell of the harbor in late winter. He was 61 years old and had lived through small earthquakes his entire life, the way everyone on the Senriku coast lives through them, with the mild inconvenience of someone adjusting to turbulence on a familiar flight. What started at 2:46 was not that. The shaking came from the direction of the open ocean and built in a way that Watanabe later described in a newspaper interview as, like something very large deciding to move. The dock swayed. He grabbed a mooring post. The shaking intensified rather than fading. Boats knocked against each other in the harbor. Buildings along the waterfront groaned. After 45 seconds, an ordinary strong earthquake's entire duration, the shaking had not diminished. It continued. 5 minutes in, Watanabe had stopped trying to stay on the dock and was simply sitting on it, unable to stand, watching the town behind him do things that buildings do not do under ordinary circumstances. The Tohoku earthquake lasted approximately 6 minutes of intense shaking. Magnitude 9.0, the fourth largest earthquake ever recorded by modern instruments. The rupture extended across 500 kilometers of the Japan Trench, where the Pacific plate dives beneath the Japanese archipelago at roughly 8 centimeters per year, accumulating stress on a fault that had last fully ruptured in the year 869. The fault moved by as much as 50 meters in places. The seafloor above the rupture rose by several meters. The main island of Honshu shifted 2.5 meters to the east. Earth's rotation changed fractionally. The day became microscopically shorter. Watanabe knew about tsunamis. Everyone on the Sanriku coast knew about tsunamis. There were stone markers on the hillsides above the town, placed by survivors of previous disasters, carved with warnings not to build below this line. There were concrete seawalls along much of the coast. Japan had spent decades and billions of dollars on coastal protection engineering, some of the most extensive ever undertaken anywhere. Kesenuma's seawall was over 4 meters high. When the shaking finally stopped, Watanabe did what the drills had taught him to do. He ran uphill. He didn't stop to gather anything. He ran to the designated evacuation site on the ridge above town and kept running until he was high enough. He turned around and watched from the hillside. The first wave arrived approximately 28 minutes after the earthquake. It came over the seawall without pausing. The barrier that had taken years and enormous cost to build was irrelevant. The wave in Kesenuma reached 8 meters in places. In other towns, Ofunato, Rikuzentakata, Minami Sanriku, waves reached between 10 and 40 meters, channeled and amplified by the geography of bays and inlets. Rikuzentakata was a coastal city of 23,000 people. When the water receded, roughly 70% of the city's buildings had been destroyed or swept away. 1,700 people died there alone. 19,000 people died along the Tohoku coast that afternoon. Most of them drowned. Some had followed the warnings and evacuated. Some hadn't heard them in time. Some evacuated to buildings they believed were high enough and weren't. Some were elderly and couldn't move fast enough. Some were emergency responders who drove toward the coast after the earthquake and were caught by the wave. The seawalls held in some places and reduced damage. In many places, the waves simply went over them. Japan, the country that had thought longer, harder, and spent more money on tsunami preparedness than any other nation on Earth, lost 19,000 people in 40 minutes. That number is the one geologists and emergency planners keep returning to, not as a measure of failure, but as a measure of scale. Japan did many things right. The earthquake detection systems worked. Warnings went out within 3 minutes of the rupture. Most people in the affected zone knew what a tsunami was and what to do. Many survived because of that knowledge. The death toll in a comparable event hitting a less prepared coastline would have been vastly higher. And still, 19,000 people died. The scale of the Tohoku earthquake exceeded what the hazard models had predicted. Not beyond what the geological record suggested was possible. Researchers had warned in papers published before 2011 that a major Tohoku tsunami was overdue, citing evidence from the 869 Jogan earthquake. But beyond what the engineering and emergency planning infrastructure had been designed to handle. The seawalls were built to defend against a wave category that the actual event exceeded by 2 or 3 times. And then, 9 kilometers inland from the coast, the wave reached the Fukushima Daiichi nuclear power plant. The plant had been designed to withstand a tsunami. Its designers had calculated the maximum probable wave height for the site and built a seawall accordingly. The seawall stood 5.5 meters tall. The wave that arrived on the afternoon of March 11th was between 13 and 15 meters. The seawall was not a factor. In the town of Futaba, 2 kilometers from the Fukushima plant, a woman named Setsuko Izumida had lived her entire life. She was 73 years old.
Her family had farmed rice on the same land for 3 generations. The morning of March 11th, she'd been preparing lunch when the earthquake hit. She and her husband sheltered under their kitchen table through the shaking. When it stopped, they gathered documents, medicine, a change of clothes, following the earthquake preparedness advice they had spent decades internalizing. They had prepared for earthquakes. They had prepared for the possibility of tsunami, though Futaba sat far enough inland that the wave itself did not reach them. What they had not prepared for, what no amount of personal preparation could address, was the order that came from the government 2 days later. Evacuate. The plant had lost power. The cooling systems for the reactor cores had failed. Explosions had occurred. Radiation levels were rising. A 20-kilometer exclusion zone was being established.
Setsuko Izumida and her husband left with what they had gathered the morning of the earthquake. They went to a relative's home in a nearby prefecture, then to an evacuation shelter, then to temporary housing. The rice fields, the house, the land that 3 generations of her family had worked, all of it sat inside the exclusion zone. All of it was inaccessible. Nearly 160,000 people were evacuated from the Fukushima exclusion zone. Studies conducted in the years following found that the stress of displacement, the loss of community, and the psychological burden of uncertainty about radiation had measurable health consequences across the evacuated population, consequences that, in some analyses, rivaled the direct health impacts of the radiation itself. The earthquake generates the tsunami. The tsunami disables the plant. The plant's failure displaces 160,000 people, and the displacement itself becomes a source of harm that extends for years. Fukushima added a new layer to the risk calculation for every coastline on the Ring of Fire. Coastal infrastructure, not just homes and roads and hospitals, but power plants, industrial facilities, chemical storage, sits within reach of subduction zone tsunamis at dozens of locations around the Pacific. The question Fukushima forced onto the table was not just, what happens to people when the wave arrives? It was, what happens to the systems people depend on? And what are the cascading consequences when those systems fail? That question does not have comfortable answers anywhere on the Ring of Fire, and the people who live closest to the next megathrust rupture mostly don't know they are those people. Drive through downtown Seattle on an ordinary Tuesday. The coffee shops are full, the tech campuses are busy, the waterfront along Elliott Bay is crowded with tourists and locals. Beneath the city and its suburbs, the Cascadia Subduction Zone is locked and loading. The Juan de Fuca plate presses against the North American plate at roughly 4 centimeters per year. The last full rupture was more than 3 centuries ago. The recurrence interval, based on Atwater's sediment work and subsequent research, averages around 500 years, with significant variation. Some ruptures have occurred as close together as 200 years. The modeling of what a full Cascadia rupture would do to this region has been published in scientific papers, presented to state legislatures, and reported in major newspapers. The shaking in Seattle from a full rupture would be sustained and violent. The city sits on sedimentary soils that amplify seismic waves, a well-documented phenomenon meaning the experienced shaking could be significantly more intense than the raw magnitude suggests. A substantial fraction of the older building stock would be expected to suffer serious structural damage. The bridges across Lake Washington and the Ship Canal are not all built to current seismic standards. The water and sewer systems run through pipelines crossing fault zones and liquefaction-prone soils. Emergency planners estimate that large parts of the city's infrastructure could be non-functional for weeks to months after a major rupture. For the communities on the coast, on the Olympic Peninsula, along the Oregon coast, on the beaches of southwestern British Columbia, the first tsunami waves could arrive within 15 to 20 minutes of the shaking stopping. The inundation zones extend kilometers inland in some areas. The
The coastal highway runs through many of them. Hospitals and emergency response facilities in several coastal towns sit inside the inundation zones. Evacuation routes in some communities amount to one road in and one road out, across terrain that may be impassable after a major earthquake. Emergency planners in Oregon and Washington have worked on these problems for years.
Some communities have vertical evacuation structures, reinforced towers designed to provide refuge above tsunami wave heights for people who cannot reach high ground in time. Drills are held, educational campaigns are run, progress is real. And still, when you compare the scale of the risk to the scale of the preparation, the gap remains large. In Lima, Peru, the arithmetic is different, but no less stark. Lima is a city of over 10 million people sitting directly above the Peru-Chile Trench, where the Nazca Plate is subducting beneath South America. The city has experienced major earthquakes historically. A magnitude 8 in 1746 destroyed much of the colonial city and generated a tsunami. The fault is active and locked. Much of Lima's population lives in informal settlements built on hillsides and river valleys over decades of rural to urban migration. Many structures have no seismic reinforcement. Several sections of the fault offshore of Lima have not produced a major rupture in historical time and may be accumulating significant stress. In Vancouver, British Columbia, the situation mirrors Seattle's closely. The city sits above the same subduction zone on similar soils. The Fraser River Delta, where much of suburban Vancouver is built, is low-lying and composed of river sediments that would liquefy extensively in a major earthquake. The highway and rail connections between Vancouver and the rest of Canada run through mountain passes vulnerable to earthquake-triggered landslides. A full Cascadia rupture would not be a local emergency. It would be a regional catastrophe, affecting two countries simultaneously, overwhelming emergency response systems across thousands of kilometers. The scientists who map these risks spend their careers in a peculiar position, publishing papers and giving presentations about events that haven't happened yet, hoping their findings will change the behavior of governments and city planners, knowing the historical pattern suggests it probably won't. Not until the event they have been warning about actually occurs. Among those scientists are researchers whose work operates at the most fundamental level, reading the geological record itself, extracting from sediment cores and ancient forest what instruments could never capture, because the events they document predate the instruments by centuries. Joanne Bourgeois at the University of Washington has spent decades studying the deposits left by ancient tsunamis, the layers of sand and gravel that a tsunami carries inland and deposits as it loses energy, visible in cores drilled from coastal soils, in sections exposed in riverbanks, in the sediment records of coastal lakes. Her work, and the work of the small community of researchers in paleoseismology more broadly, operates like forensic science applied to deep time. Pull a core from the sediment of a coastal lake, and you are extracting a record. Layer by layer, pollen from surrounding forests, the remains of microscopic organisms, the gradual accumulation of fine sediment from normal weather and runoff. And then, sometimes, a layer that doesn't fit. Coarse sand, shells, marine organisms that have no business being in a freshwater lake, deposited suddenly in a single event. The signature of a tsunami. The date can be estimated from the organic material in the layers above and below, from radiocarbon dating, from pollen chronology. Working with that kind of evidence, researchers have extended the seismic record of the Pacific coast back thousands of years, far beyond the reach of written history, far beyond the memory of any living person or institution. What that extended record shows is consistent and sobering. Cascadia has ruptured repeatedly. The deposits are there, layer after layer, in lake after lake. Each rupture left its mark. The pattern is clear. The only uncertainty is timing. A graduate student working in this field once described the experience of pulling a core and seeing a tsunami deposit appear in the sediment as finding a witness statement from an event no one survived to describe. The gray sand in the core is information. It is the ocean speaking across centuries in the only language it has available. And the message it carries is always the same. This has happened before. The physics that made it happen are unchanged. The clock is running. The warning systems the world has built since 1960, since the Chile tsunami crossed the Pacific and killed people in Japan, since the 2004 Indian Ocean disaster showed the cost of having no system at all, represent genuine progress. They are real, they function, and they have already saved lives. The Pacific Tsunami Warning Center in Hawaii monitors seismic activity continuously. Deep ocean assessment and reporting of tsunamis buoys, the DART system, are anchored across the Pacific, equipped with pressure sensors that detect the subtle signature of a tsunami wave passing overhead. When a buoy detects a wave, it transmits data by acoustic link to a surface buoy, which relays it by satellite to the warning center. The system can confirm a tsunami is in the water, not just predicted from seismic data alone, within minutes of a major earthquake. Japan has gone further than any other country. After the 2011 disaster, the Japanese government commissioned a complete reassessment of tsunami hazard along all of its coastlines, based on worst-case geological scenarios rather than the historical record of recent centuries. The results led to revisions of inundation maps, reconstruction of seawall heights at many locations, and substantial public investment in vertical evacuation infrastructure. Towers, elevated platforms, reinforced buildings designated as tsunami refuges. The culture of tsunami awareness, already deeply embedded in coastal Japanese communities, was reinforced with new urgency. And yet, the warning systems carry irreducible limitations that no amount of engineering can fully overcome. In the event of a near-field earthquake, one close to a densely populated coastline, like Cascadia near Seattle, or the Nankai Trough near Osaka and Tokyo, or the Peru-Chile Trench near Lima, the time between the earthquake and the arrival of the first tsunami waves may be 15 minutes or less. In some locations, under 10. The warning systems can issue an alert within 3 to 5 minutes of a major rupture. That leaves, in the best case, 10 minutes from the moment someone's phone buzzes to the moment the water arrives. 10 minutes across terrain that may already be damaged. 10 minutes through communities where power and communications may already be gone. 10 minutes is not enough for everyone. It never has been. And the systems we have built cannot change the underlying physics. What determines survival in a near-field tsunami is not primarily the quality of the warning technology. It is whether the people who need to move already know exactly where to go, are physically capable of getting there, and are not obstructed by a landscape the earthquake has already damaged. Those factors depend on years of preparation, public education, infrastructure investment, and community planning. Things that take decades to build and must be maintained continuously in the absence of a recent catastrophe to supply motivation. This is the fundamental asymmetry of living on the Ring of Fire. The geological hazard accumulates on timescales of centuries. The political and institutional will to prepare tends to accumulate on timescales of electoral cycles and news cycles. The fault doesn't care about budget cycles. The stress builds at exactly the rate the physics dictates, whether or not the legislature is in session, whether or not the most recent earthquake is within living memory. There is a stone in the Aniyoshi hamlet of Miyako on the Senriku coast of Japan. A tsunami stone, one of hundreds placed along this coast by survivors of previous disasters, each carved with inscriptions warning future generations not to build below the marker. The Aniyoshi stone dates to 1933. It reads, "High dwellings are the peace and harmony of our descendants. Remember the calamity of the great tsunamis. Do not build any homes below this point." The hamlet of Aniyoshi sat above the stone. When the 2011 tsunami came, it reached exactly to the base of the marker. Every household above the stone survived. This is what accumulated knowledge looks like when it is actually embedded in a community's behavior, rather than stored in reports that no one reads. The stone is not a warning system. It has no electronics, no satellite link, no algorithm. It is a carved piece of rock placed by people who understood that they would die and their grandchildren would forget, and that the only way to reach across that forgetting was to put the knowledge in stone at the exact place where the water had stopped. Below the stone, there is a valley. Before 2011, there were houses in that valley. The people who built them had moved down the hill because the flat land was more convenient for farming. They knew the stone was there. They had seen it their entire lives. They had decided that the risk it warned of was sufficiently remote in time to be acceptable. 12 of them died in March of 2011.
That gap between the carved stone and the house built below it is not unique to a hamlet in Miyako. It is the gap between the Pacific Tsunami Warning Center and the tourists photographing the retreating sea in Thailand in 2004. It is the gap between Atwater's buried meadows and the unreinforced buildings of downtown Seattle. It is the gap between a geological record that speaks clearly and the infrastructure that has yet to fully hear it. The ring of fire is not going to stop. The Pacific Plate will continue to dive beneath the plates at its edges. The stress will continue to build on every locked fault from Chile to Kamchatka to Cascadia. The volcanoes above the subducting slabs will continue to be fed by the water released from descending crust. The earthquakes will come. The tsunamis will come. The question that science has been asking for half a century, and that the world has been imperfectly trying to answer, is not whether. It is only when, and whether anyone will be ready. Right now, somewhere beneath the floor of the Pacific, a fault is locked. Two plates pressing against each other are accumulating stress the way a compressed spring accumulates tension. Silently, invisibly, with absolute indifference to the cities and coastlines above. The spring doesn't announce itself. It doesn't give a countdown. The only signals it sends are the slow creep of GPS stations as the overriding plate is dragged toward the subducting slab. The patterns in ancient sediment read by researchers in waders with drilling equipment. The stories carved in stone by people who watched their world unmade and wanted to reach across time with a warning. The ocean that Magellan called peaceful is the engine of this planet's most violent geology. It has been running for 250 million years, and it will run for 250 million more. We have been living on its edges for a blink of geological time, and in that blink, we have figured out what it does and why. That understanding is one of the greatest achievements in the history of science. It is also, in a very precise sense, the beginning of a responsibility. Knowing what the Earth is capable of and choosing not to act on that knowledge is not a geological problem. It's a human one. If this kind of science, the real scale of the world, told honestly, is what you come here for, subscribe and leave a comment below with the question you want answered next. The Earth has more stories to tell, and not all of them have peaceful names.